So we are DynamicCast, and what DynamicCast is, it's a peer-to-peer study group for people underrepresented in tech, and we host monthly meetups, in-person ones here in London at the Focusrite offices, but we also, it's possible to join us online, so we always share a link, so people can join us from wherever they like. At these meetups, we usually just share what we've learned or rehearse conference talks, for instance, show our projects, and sometimes we just watch and discuss talks together. So the format is mixed, and you're very welcome to suggest something else also when you join us. So if you're interested in joining us, please speak with us after the workshop. Come talk to us, we're here. We also have stickers, so please help yourselves afterwards. Lovely logo, isn't it? So, right, I think I didn't mention that it's a C++ study group. So that, explains the logo. Right. We also have a website that it's there on the bottom right corner. It's quite minimal, but you'll find our Twitter handle and an email address there in case you want to contact us later. Okay, so today's workshop is going to be delivered to you by Harriet, a software engineer at SoundStax, Alex, a software engineer at Ableton, Emma, QA engineer at Focusrite, and myself, I'm Anna. I'm ex-Ableton, I'm a freelancer now, and also a PhD student at the Creative Computing Institute at UAL. What else did I want to say? Right, the presentation slides are available online in case somebody wants to click on links or follow us as we go. They're on our GitHub. If you find the ADC 23 repo, we will be using it later, so you can go on and find it now. There's a wiki section, so if you click on it, the slides are going to be there. Right, just briefly, let's talk about the goals of this session today. We will give a brief introduction to the concepts and introduce some names used in audio programming, and we hope it's useful in the practical parts of the session. And then we're going to be implementing basic string synthesis in a new programming language called C Major. We will give a gentle introduction to it, don't worry. Right, I wanted also to say that we don't expect you to remember everything we say, but we just hope it helps you navigate the rest of the conference later, or some concepts you encounter in your audio development journey. We'll be taking questions also online, so please feel free to post them on Zoom. I'm on a Zoom call, so for the online participants, just post them there or on our Discord channel. There's a Discord channel, it's called DynamicCast Workshop something. Please find it and post questions there. We can be taking questions in person when the speaker is ready to answer them. And if you need assistance, just indicate it. We'll come help you out. I think this is it. Let's move on to the first session. I'm going to hand over to Alex, who's going to take you through take you through the way how signals flow through audio systems.
Hello. All right, so let's start with the basics. What is it that we're talking about when we talk about digital signal processing as it applies to audio? So first off, what is a signal? Put simply, a signal is a parameter that changes as a function of another parameter. Usually it's time or space, but it also can be another observable variable. In the case of sound, it's going to be the amplitude of a sound wave changing as a function of time. We may be talking about a physical representation, which is a measure of sound pressure changes, or if we capture the physical sound using a transducer, such as a microphone, we obtain an electrical representation, a measure of voltage changes. Both of these signals are continuous, but computers can only operate on discrete signals. So in order to process sound on our computers, we need to discretize it. This is done through a process called sampling, which is performed by a digital to audio converter, to analog converter, analog to digital, I mix it up, which turns voltage variations into a numerical stream. And each sample represents the value of the signal at a certain point in time. We won't be going into the details of that process. It's a practical workshop, so let's not be too heavy on theory. What's important is that we're left with a signal that is no longer continuous. And we can also generate those samples artificially, that is, synthesize them, for instance, using a digital oscillator. All right, so what is it that we can do with a signal? First of all, we can scale a signal, which means multiplying it by a constant scaling factor, such as when we use a gain control to either attenuate or amplify the output sound. We can also do time scaling, also called dilation, which will cause a signal to either compress or expand, which could be used to change the duration and frequency of the sound. Another possible operation is a time shift. Shifting a signal in time can be used to introduce a delay. We can also do time reversal, which is like playing something backwards. And when we're dealing with multiple signals, we can first of all perform summation. So we take two or more signals, and that is equivalent to audio mixing. We could also multiply the signals, such as when we turn a constant signal into an envelope and apply it to an audio signal to produce a note. And of course, other more complex functions can be applied and combined to create arbitrarily complex DSP systems. A DSP system is any process that produces an output signal in response to an input signal, with some manipulation of the input signal occurring in between. An example of a continuous system is an analog synthesizer, and a software synthesizer works as a discrete system. So the synthesizer might take a generated audio signal and an envelope signal as an input, and then pass the audio signal through, let's say, a filter or an amplifier, and then combine the processed signal with the envelope, which gets triggered by a button or a key press to produce output audio. The result of this process can be then sent to a loudspeaker and transformed back into an audible sound wave. And maybe as a side note, one thing that's worth noting with regard to mathematical notation that we're using here is that for continuous signals, we tend to use parentheses, as with this x of t. And for discrete signals, we use square brackets, as shown for x of n. And this kind of data and transformations that we've been talking about lend themselves particularly well to a modular processing architecture. So a module encapsulates a certain signal transformation, performing any number of signal operations depending on what they're meant to achieve. And each module is connected to one or more modules coming before and after it. In some particular implementations of this architecture, it's possible for the connections to be freely rearranged, which allows for a lot of flexibility to test out different topologies quickly. An analog example that comes to mind is a guitar effect chain. So each pedal takes an input either from the raw unprocessed signal coming from the guitar or the result of the processing done by the preceding effect. And then it then applies its own modifications and sends its output further through the chain until it finally reaches the amplifier. These processing systems can, of course, be as simple or as complex as necessary to produce the desired effect. So while guitar chain effects are usually linear and often consists of just a handful of modules, modular synthesizers, on the other hand, with the tangles of patch chords and that split and multiply and sum the signals, present a much more elaborate structure. And when you connect the modules with patch chords to produce a certain sound, the particular pattern of connections which produces that sound is known as a patch. And we also refer to these sounds themselves colloquially as patches. And now, as intuitive as this paradigm seems nowadays, this concept of modular processing wasn't translated into the digital world until the 1960s, at which point experiments with software synthesis were already well underway. And it was only in the 1960s that Max Matthews, who's widely considered as the father of computer music, came up with this idea of applying these modular building blocks to sound synthesis software. So he devised a programming language called Music 3, which allowed its users to create networks of so-called unit generators, or UGs, which modeled, for instance, virtual oscillators, envelope generators, filters, amplifiers, what have you. And they could be interconnected in arbitrary ways to create an instrument or, again, a patch. And the flexibility of this design meant that a variety of synthesis algorithms could be implemented relatively easily. Music 3 was just one in what became known as a family of Music N languages, all of which are based on this idea of unit generators. The legacy is preserved in modern implementations of this architecture, both visual, such as Maximus P, PD or Audio Mulch, and also textual, such as Super Collider, Chuck, Faust, and C Major, which is what we're going to have a look at today. And this modular graph architecture, maybe as a side note, is also mirrored by how many audio applications developed with general purpose programming languages are organized internally. And again, the patches can be as simple as or as complex as desired. And for instance, here we have an example of a Max MSP patch that outputs a sine wave of different frequencies. I hope I can get my mouse where it should be. Let's see. Nothing fancy. As simple as it can be. And, oh, hang on. Can we stop that? Yeah, and here we have another patch, which is an implementation of an FM synthesizer, a vastly more elaborate one. Let's check that out. That's what it looks like, right? Can I move on? Right, so I will now hand over to Anna, who will tell us a little more about the programming paradigm, which all of these languages I mentioned are based on. So.
Thank you. Just one more concept and we're off to coding, I promise. So bear with us. Right, so all these languages that Alex mentioned that we'll be focusing on one of them later, use this paradigm called data flow paradigm. And now we're going to take a closer look at why it's called this way and how it differs from the so-called imperative paradigm, which you all are probably more used to from your experience with other popular programming languages like C++ or Python and so on. Right, so what is data flow programming? The most important quality of it is that it models a program as a directed graph. So we focus on the movement of data, model programs as a series of connections then. And graphs, it turns out, are a great way to represent data dependencies, which is gonna come in handy. So here on the slide, you can see an equation that includes a summation and then a division and then a multiplication of the result expressed as a graph, right? A more formal definition of what a directed graph is, according to the graph theory, is that it's a collection of nodes connected by arcs, simple as that. And both node and arc can be substituted by other names that you'll sometimes maybe encounter, like vertex and an edge, and point and connection. But in the context of directed graphs, the most commonly used term is node and arc, so we're going to be using this one. And a directed graph is a specialization of an undirected graph, where connections have explicitly defined direction. So we have nodes, arcs, and direction, right? That's most important. Right, so what does each of these elements mean? A node is basically a unit of computation, and it can be as small as a single machine level instruction, like a multiplication seen in the example, or a function of arbitrary complexity. And a node can take one or more inputs and produces one or more outputs. So you can see that it's a good metaphor for what Alex was saying about the building blocks of a modular system, right? Pretty good metaphor. Right, we also have arcs, which are basically pipes through which data passes, and they express the data dependency between nodes. Sometimes you'll encounter the term token, and it basically means a unit of data of any type you may like. And port, if you ever encounter it, means a boundary between the node and an arc. We have input ports and output ports, and just many times this term will be discarded and we'll just simply be saying inputs and outputs, or input arcs, output arcs, input connections, output connections. Right, so in pure data flow, ports are the only way to get data in and out of a node. So global variables are not allowed, which also means that nodes in a data flow graph don't modify any state variable outside of its local environment. So they don't have side effects, we say in functional programming, right? That's gonna be important in a second, I'll tell you why. Okay, you'll encounter different types of nodes. These are gonna be the terms you're gonna be seeing also later in the workshop. So nodes without input ports are gonna be called inputs or sources. And you can think of audio stream generators, like, for instance, oscillators producing signals like sine waves, or audiophile readers. They're going to be inputs. The nodes without output ports are called outputs or sinks. And these are nodes that can prepare audio samples in their final audible form or save data into a file, for instance. The rest is going to be considered as processors. And processors are nodes which basically perform operation on data, typically changing it as a result, right? So the data coming in is going to be different from the data coming out. But they could be so-called monitoring nodes, which don't alter the data. They just maybe plot it or analyze it in some ways. All right, so as we said earlier, graphs are supposed to represent data dependencies. It's a data-driven model. And therefore, nodes only get processed when they receive all the data they depend on. Only then they are ready to be processed. So let's see how, what are the implications of that, and how this model differs from what we're used to when dealing with the imperative languages, as I mentioned before, like C++ or Python, JavaScript. So as we said before, in the data flow model, we follow data and then trigger actions, right? All data arrived, we trigger an action. In imperative languages, we follow a very explicitly defined sequence of instructions. So we focus on a very explicitly defined control flow. So in an imperative model, data may follow the control flow, but the main question is about the order of execution. And in the data flow model, control follows the data. And computations are executed based on data availability. So that's the main distinction. These are like different ends of a spectrum, right? So imagine the scenario from the graph on the slide. And imagine input B being ready while we're still waiting for input A to be prepared, right? Maybe it's a large, I don't know, vector being loaded and taking its time. So in this situation, the division node is already ready to activate, whereas we have to wait for A to be able to perform summation, right? And in the imperative scenario next to it, this like pseudocode written on the side, it becomes clear that we have to first wait until all data becomes available to perform the first computation if we defined summation as the first one, right? So we can see that in this scenario, the data flow model gets a head start, clearly. So this also means that the data flow model reveals quite naturally opportunities for parallelism. It reveals early when all data dependencies have been satisfied, and we know sooner when it's okay to launch a parallel operation. And again, as I mentioned before, all data is supposed to be local. All data is local, so we naturally tend to prevent styles of memory access that would prevent parallelism. So that's a really good advantage of this kind of a model. But there are also some drawbacks to this approach, and probably people who have experience coding, like making patches in MaxMSP or pure data, know how tricky and inflexible it is to write any control flow operations like looping and so on. It's quite tricky, especially in visual languages. And in this slide, you can see a factorial function implemented in the imperative style in Python to the left, and in the data flow style on the right-hand side. So we can see that implementing an algorithm like a factorial of computing a factorial of a number is a pretty good task for an imperative coding style. It's pretty straightforward. You see two versions of it here, using recursion and without it. So why would we want to force ourselves to do it in a data flow style, right? That's actually quite cumbersome. Well, what if we could combine both? And if we combine both, we reach a hybrid data flow. And then we would write our computation in the imperative style and stuff it in a node. And then we use this node as a closed box in our data flow graph. So still a good analogy for the modular setup of like audio systems. Right, so the hybrid data flow is actually the approach that we see in modern solutions to problems which can be solved on a directed graph most commonly. So again, directed graphs are good for representing dependencies or scheduling execution of parts of the computation unit, of like some of the computation units. So this is why we see them commonly in audio engines. We have audio graphs being processed. We see them in libraries for parallel computing of big data. The web audio API is modeled using the concepts we've described, so maybe if you ever deal with it, it's going to be easier to understand. Also, TensorFlow, actually a popular library for implementing and deploying large-scale machine learning models, uses directed graphs internally to represent computations. Right, and as we said, C major is going to have a similar syntax, so hopefully it's going to be easier to understand what's going on. So now I'm going to hand over to Harriet, who's going to start with the practical part, and I just hope this introduction will make it easier to follow it later.
All right, thanks guys. Thanks for that introduction as well, it was lovely. If anyone needs a break at any point, please don't feel scared to do that, just let me know. I'm happy to do it. So what I want to do now is give it's a bit of a sneak peek to this afternoon's workshop if anyone's coming along to that. We're using C major today because we found it a simple way to sort of show the DSP that we want to do in a sort of, and also, I mean, I might be a little bit biased, obviously. So, C major, what is it? Maybe you saw our announcement talk last year at ADC, or you maybe are aware of C major already. It's basically a C-styled language that's designed for DSP signal processing code. So we have some like main aims and targets that we had for this year. So our main aim is to match/beat the performance of C/C++, be simple enough to learn, which is why we're doing it today, to entice people to use it, and also make code portable across processor architectures. So we want to support like CPUs, GPUs, DSPs, TPUs, like et cetera, et cetera. We also have some nice extensive tooling, so we can compile to WASM, CLAP, JUICE projects, and this is like an ever-growing list of things as we keep going. So we use an LLVM JIT compiler for all the nerds out there who are interested to optimize, and that means we can hot reload code as well. So that means we can change the patch in a way, or maybe we add a new gain or something. I can press Control or Command S, and we can see it reload in real time and stuff. If you want any more information, have a look at the website. that will go into a bit more depth than what we will do today. So the tool I'm going to use, and maybe the easiest way to get started with CMajor, is downloading VS Code and using our CMajor extension. We don't obviously just use this, we support whatever platform people want to write with, but this actually internally uses our command line tool to create a VS Code panel with information about your CMajor patch. I would implore you to use this today with the workshop simply because we're going to be working with synthesis and it's got a keyboard on screen so you can make noises from your laptop without needing a keyboard. Yeah, so I can show this if people need, or maybe we should take a 5 or 10 minute break after I've finished explaining. We can go through all this as well. There's also the command line tool, which you can install directly from our CMajor repo. And if you go to our latest releases tabs, you'll find it there. Yeah, please feel free to go along with this or go ahead and just start playing with that now as I'm sort of talking through some main concepts. So let's have a look and let's have a quick summary of like the main concepts in CMajor. So we have this idea of a patch, and this is like a bundle/folder that contains all your metadata files, program files, and like other resources such as like GUI scripts and audio files if you're doing a sample play or anything. And as Anna was mentioning earlier, we have this idea of processors and graphs. So we can call to sort of nodes within, it's like a processor, and we can call that within a graph, and then we can connect them in a sort of line-by-line way to do that sort of architecture. Brilliant. Yeah, so processors declare a main function, which I will go through in a bit. And that contains a loop, which reads inputs, performs some processing, and then writes outputs and repeats. And it's an infinite loop, so that'll constantly repeat throughout the remainder of your program. So here's an example graph, very quickly. I will talk through every single bit in a minute. As you can see, as Anna was saying, we declare our inputs and outputs, and we're using a float type for this. We've got 2 gains. Why not? We're doing 2 different gain things. And then we connect them at the bottom here. So we've got our connection in. This will just be from whatever microphone you've got on your laptop. Go through the 2 gains and come back out. And here's an example processor doing the same thing. So we've got our inputs and outputs. That's the test. Nobody worry. I guess I'll wait.
If it goes off again, it's real fire.
Yeah, if it goes off again, please leave. But is anyone on fire right now? No? Okay, cool. We can keep going.
You're on fire.
I'm on fire. Nice. So this is the example processor basically doing the same thing, but I've just used 1 gain this time instead of 2. We've got our inputs and outputs. We've got this sort of main, and we go into our infinite loop. We're timesing our input.
Is it fire now?
Is that a real fire or not?
Probably not.
Probably not, right? Is that... I mean, that's the thing you want to say, right? Like, we might burn, but we might not also, so it's fine. The Thames is there, we'll be fine. Yeah, so read in and read out, and then we advance to the next frame. So let me just go back to previous slides quickly. So you'll see here we've got the input stream and output stream, and I just want to sort of define that a little bit better. So this is how processors and graphs communicate with the outside world. They communicate via these endpoints, and they must always at least declare 1 output. They don't have to take an input, but they should, well, they have to take an output. So we get the, hang on, I'm just going to make this a bit bigger on my screen so I can actually see the slide. We sort of define the syntax to be like a direction, so you're inputting or outputting, the type, so we've obviously got floats and ints, et cetera, et cetera. Stream type even. Stream, event, or value, and then we declare if it's a float, an integer, et cetera, et cetera. We give it a name, can give it an array size if wanted, and then we have some optional annotation that can be used to sort of make some on-screen sliders and such. Yeah. So I've only shown the stream endpoint so far. So this transmits a continuous sequence of sample accurate values, providing 1 value per frame. So the type of stream must be scalar, so it must be a float or integer, or a vector of floats and ints, so they can be summed, basically. Streams involve storing, updating values at every frame, so we work frame by frame with this sort of methodology, which makes them quite computationally expensive, because this is something that happens all the time. So this makes them a bad choice for sort of values that rarely change. So if you've got like a button on screen that's just sort of like selecting a mode, you can use a value or an event endpoint. So a value endpoint does that. So it can hold any type of data, allows for a fixed value to be sent or received in a way that's not sample accurate. they have like effectively zero overhead when the value's not being updated, so it will listen for a change in the value that's happening, basically. And then we've got the event endpoints that sort of act in a very similar way. And in fact, I find personally that events and values are sort of interchangeable and you can use them to do similar things. When you declare an event handler, you have to use the name and type to match the endpoint. So you have to do the special sort of event loop bit, and you can do something with your input here. If you've got like multiple types within your event, like a string or a float, you can do multiple event loops for this. So I thought I'd show you some C major patches first before we do anything, but would we like a quick break to get everyone up to speed with VS Code? What do you guys think?
Yeah.
Everyone okay? Or should we take a quick 10-minute break? What do you think, guys?
Let's start coding now.
Let's start coding.
Just
Let's do it.
half an hour.
Okay. So what I'm going to do now is switch the display type so I can actually see what I'm doing.
There's Wi-Fi here if anybody needs it.
Okay. Yeah. Good question. Do I want to start with this one? Yeah. All right. Has everyone got C Major installed, or are people going to do this while I talk? Any thoughts or vibes? Questions? All good?
Okay.
Still installing. That's fine. What I'll do is I'll talk through these examples and then we'll just take a quick 5-minute break and I'll just come around and make sure everyone's set up and got everything that they need. This is the first patch I wanted to show you. This is first of all, can everyone read this? I can make it a bit bigger if need be. Is everyone good? Maybe that's better. All good at the back? Brilliant, fantastic. So this is using the topology that Alex and Anna explained before. So we've got this graph that's sort of taking in our input, taking in our output, and then we're going through this gain processor to put an arbitrary value through to make a gain, basically. What I want to focus on here is the topology of the graph. So first of all, we declare our inputs, then we declare our outputs, and then we've got these nodes. So nodes are generally how you instantiate a processor within a graph. So I could add to this example. So I could have node gain 2, and I will make this equal the gain processor below, like that. And then that means I've got another instantiation of this. So I could connect this in. There are some fun syntax things we can do here with the connections and stuff. What we've got going on here is we're going into the input stream of gain processor, and then we're doing our sort of DSP, our maths, and then we're coming through our output stream to go out. Nice and simple. I just wanted to show this as an example to highlight. I'm just going to mute my sound for a second so I don't get a feedback loop when I run this patch. So if I now run this patch in our VS Code panel, just give it a minute. Okay, great. So this is our VS Code panel. Looks weird at this font, this size. As you can see, we've got this gain knob. I'm sure if people are playing on it right now online or in person, you can hear a difference in your microphone. And you can see our input here, so we know it's working. I can actually input a file here as well, so we don't have to listen to just yourself talking. And then we can also monitor the outputs. What I wanted to show here was this graph topology. So you can see we're taking our input stream, which is me talking right now. We've got our gain value, which is coming from sort of this knob here. It's 0.86 right now. We're going into our gain processor, and you can see it's sort of named after the node, and then it tells you which processor that is, just for ease. It's doing our DSP, it's doing our summation, we're getting our output, and we're going straight through to the out. And that's maybe the most simple gain I could make while showing something. So let's go into the second gain processor here. So what I've done here, actually, yeah, I'll explain that first. So what I've done here is use the input value. This is what I was talking about earlier. So I've made 2 patches that do the same thing, but the first one uses an input value and the second one uses an input event. And as you can see, I've annotated this input value. And when it gets updated in the patch, when someone moves that knob, it will update. It's computationally inexpensive, and then that's how we get our value. So gain processor 2 here we're doing the same thing. I've annotated the event. We've got an input event, but instead of going through this main loop with just the value, you have to actually assign it using this event endpoint here. So the topology of the main graph is the same. The only thing that's changed here is we're using an input event. And we should see the same thing here as well. If it wants to load, of course. There we go. Exact same. We've got a knob initialized to 0.5. We're obviously not going to go above 0.9 because if we go to 1, we're going to get an infinite feedback loop, which would not be nice. And the exact same thing. We've got our in, we've got our gain. We go into our gain processor. We output our audio stream. Amazing. So what happens if you want to generate something rather than just make something a bit louder? So this is our annoying beep patch. And as you can see, I've only used the gain here. So what we've got in the standard library for C major is a method to make sine waves, and you can sort of define the frequency. So what I've done is I've made a node again, which is calling to a processor. It's going to std oscillator sine. I've told you that I want a float type, and I want it to be 440 hertz. I've added a smooth gain as well, just because it sounds a bit nicer. And we'll play this for you now. Bearing in mind, I don't want to damage people's eardrums. And as you can see here as well in the topology, there we go. We've got our wave. I can change the volume so it's not so annoying. Or I can make it more annoying. I can change the frequency. Like so. Now let's get rid of that because it is an annoying beep. But as you can see here, as I was going to say, so in this graph topology, we're not taking an input stream from the user. So we're passing in values to the gain of the gain node and the frequency to the frequency node. So that just makes those knobs on screen that we can edit. And then again here, we've got connection into the gain in, gain out, nice and simple. And then the final example I wanted to show you is 2 gains in series. It's the same thing basically, but the nice thing about this is just showing that we can do all the connections in one line. So if you're not declaring a specific endpoint, if you've only got one endpoint, you can actually just go in to gain 1, to gain 2, to straight out. Okay. So I'm just going to make a new folder quickly and just put ADC. So when you're working in VS Code, what you're going to want to do is it's Command-Shift-P on Mac, it's Control-Shift-P on Windows, and type in C major. And what you're going to need to do is create a new patch. Create it without GUI, obviously, for now. And I'm going to place this in my folder here. And I'm just going to call it hello. The reason I'm getting you to do this is because you need this .cmajor patch file to actually run the C major file. So this .cmajor patch file is sort of JSON styled. It's a manifest file basically, and it tells you where to find the source code. I'm very sorry, I completely forgot to introduce this. It tells you the source code, where the location, which is here. But to actually execute a patch, you can have this page open, but you're going to need to have this .cmajor patch manifest in the same location as the .cmajor file. So when I run this patch, it's loading the .cmajor patch file, which is this file here. That's my bad. And we've got another annoying beep. Brilliant. Okay. Continue playing, I guess, for a minute. So I've picked quite a simple sort of synthesis idea to give this workshop. I thought it might be cool to sort of show some MIDI, make a noise, and just make a big racket, basically. So this is a diagram of the Karplus-Strong string synthesis idea. So the Karplus-Strong synthesis algorithm, it's a method for generating realistic plucked string instrument sounds. This might be something like a guitar, a banjo, or instruments that are similar to that. It was developed by Kevin Karplus and Alex Strong in the 80s. And what we're doing here is we're emulating the physical properties of a plucked instrument. So this algorithm is like basically an example of a physical modeling synthesis. So before I explain that diagram, I just want to show you, this is my really crude example of a guitar, but from the side. So I made this in Miro. It was It took me 10 minutes. So what you can see here is I've made this very over-exaggerated plucked string position. So if you think about you're holding the string up with your finger or with a plectrum, probably not to that angle, because you probably won't have your string in tune. What you're doing is you're bringing it to this plucked position. You're giving this initial excitation or burst of energy. And then what happens from there is you'll see the string start to vibrate and decay over time, basically. So this is what this sort of simple-ish diagram is showing. We have got this input noise source. This is what we're replacing with the plucked string. And then we're going to feed it back on itself, and we're going to decay it over time slowly to make this sort of sound of like an outputted guitar, basically. And this is where I was going to have a break, but we've moved on. There's just one more thing we want to talk about before we go into this, because we want to sort of discuss MIDI and stuff, is control and interaction. Alex, are you the one leading this one? So I'm going to pass back to Alex, who's going to give us a quick overview of controls, interaction, and MIDI. Okay.
Hello again. So there's one more topic I'd like to talk to you about before we dive into the code, and it's about control and interaction, as Harriet said. So what is an electronic instrument good for if we can't control it? We can have an instrument output a constant sound or a processor repeat the same processing pattern, but that gets a little boring after a while, right? So musically interesting effects arise from variations occurring over time that surprise our brain by breaking expectations. Thus, we want our real-time audio systems to be interactive. So let's have a look at how this interaction can be made possible. So apart from signal inputs, unit generators in a processing system can also accept control events as input. We can distinguish between events that provide a way to alter the parameters of the module or provide timed information about notes that are meant to sound, their duration and pitch. This note information can be supplied either by a user performing on a device, a controller, or supplied by a sequencer or a DAW, in form of a score. And how this data is formatted is dictated by the universally adopted MIDI standard. And since we'll be implementing a MIDI gate later on, let's take a closer look at it. So MIDI stands for Musical Instrument Digital Interface, and it's a communication protocol. It was invented to enable musical devices and computers to pass data in a standardized way. And while it was initially designed with hardware communication in mind, be it synthesizers, drum machines, or just controllers, it is also used to transmit information in purely software contexts. The data that is passed is not inherently musical, but represents a set of control instructions for controlling a musical device in real time. Whether that's information about the notes that are being played or controls for parameter manipulation. MIDI data is packaged into messages of various types, which encode different aspects of musical performance. So let's have a closer look at what kind of messages can be sent and how they are built. So MIDI messages are sent as a time sequence of one or more bytes, and they consist of a status byte, which is always first, and it serves to describe the type of the message being passed. And it may be followed by a number of data bytes that describe additional parameters. How many depends on the message type. MIDI messages can be divided into two categories: channel and system messages. Channel messages are destined for a particular channel, while system messages are broadcast to all connected devices through all channels. Channel messages include note-on and note-off messages that communicate which notes should either start or stop sounding. And these are the messages we'll be mostly concerned with for the purposes of this workshop. And there's also pitch bend control, which allows for a more fine-grained control of the pitch. And then we also have control change messages, which transmit information about gestural changes to modulation wheels, volume pedals, encoders, faders, and other controls. Finally, there are also program change messages for communicating a selection of a different patch. And the two types of system messages include system exclusive or SysEx messages, whose purpose is defined by the device manufacturer. And there are also system real-time messages, which are clock messages for synchronizing devices. Now let's take a closer look at a note on message. It's a 3-byte message, and as every MIDI message, it starts with a status byte with the code 1001 in this case. And the last 4 bits represent the MIDI channel used for routing the information to specific devices. The status byte is followed by 2 data bytes, where the first data byte encodes the pitch value, and the second one, the velocity value, which controls the amplitude, so how loud the note is going to be sounding. A note off message is very similar, with the exception that the code is 1000, and the meaning of velocity is also a little different, since the given note that this message is targeting is meant to stop sounding. So it can no longer describe the loudness of the note, and instead it refers to the speed with which the note is meant to be released. One thing that merits a comment here is what kind of pitches are represented by these messages. So we've got 7 bits, and 7 bits allow for a range of 128 numbers to represent pitch. And the MIDI specification prescribes that these values map to equal tempered pitches. We can use pitch bend to escape that limitation in combination with MPE, or MIDI polyphonic expression, which is an extension of MIDI. And naturally, we don't want to deal with raw MIDI messages in our programs. That's not very fun. So for general purpose languages, there exist libraries for parsing MIDI messages, and many music-specific languages, such as C major, also offer libraries with abstractions that provide a friendlier interface to the information encoded in MIDI bytecode. They also offer converters that translate raw MIDI data into those, and further abstractions, and vice versa. That's enough from me, so I'll hand over to Harriet again, who will walk us through the algorithm.
Thank you, Alex. Hi, it's me again. You might remember me from 5 minutes ago. Okay, so I've split the section into 4 branches on our GitHub repo, basically. Do you guys want to see this thing making some noise first? Should we do that? Let me show you. It's only taken us an hour and 10 minutes to make some noise. Okay, so can everyone see that? Brilliant. Let me just bring up the font size a little bit again, because I will be going through every single patch. So this is the C major patch that I want everyone to write with me today. I will be coming around and helping. This is our implementation. Oh, what happened there? It's our implementation of Car + Strong. So this is the repo that you'll see. I've done a little bit of a README that goes into information of where things are. And then I've got a little sort of MD file that explains the very basics of this patch. But don't worry, we'll be going through all of this. Oh, you can't see my display, I've just realized. Technical issues. Keep changes, please. Okay, brilliant. And now you can see it again. Okay, so what I was saying was, so after this workshop, if you find yourself looking at the repo again, please refer back to this markdown link if you don't want to go through all the slides to sort of go through it. But I will be explaining every single bit now. So this is the patch. As you can see, we take the MIDI in that Alex just explained to us all. And we've got a nice voice, we've got a nice processor, and a note selector and a delay. So this is what we're going to be doing today. If I run this patch, it will take 1,000,000 years to load. And this is what we're going to be making today. We're not going to be making a GUI this morning, but you'll see this keyboard pop up because our tool's gone, oh, hey, you've got MIDI coming in. Wouldn't it be nice to be able to do that? So I press my keyboard. Haha, nothing comes up. Well, it works on screen, so let me check my MIDI devices. It doesn't matter. Anyway, so if you run this patch now, you'll see this, and we get this sort of string sounding thing. It's not perfect because we've sort of built a very basic thing here, but the idea of today is that we make this basic patch and you can go ahead and make changes to either make it a bit more accurate, or you can take this in a completely different way, add a different noise source and make it like a lo-fi vibe. The nice thing about writing synths is the ability to do all this stuff and add additional DSP and work with it as it goes. So this is sort of our string sound. There's quite a lot going on in that. We've got that short burst of white noise, and then we're decaying back round, and we're using a filter to take through the top end of this. Okay. This is going to get old real fast doing this extend display. There we go. Yeah, so you'll find all the branches here. If you're not set up with Git, this is something we're not going to cover today, so please just feel free to download all of this as a zip file and go through each branch as needed. Yeah, so this is our lovely diagram again, and I will be referring back to this throughout the process. So the first part of this is something I've already alluded to already. We've got this sort of noise source, and this is what we're using to replace that plucked string action. So generally in signal processing, noise is like an unwanted modification to a signal. That might be from, say, this microphone to this wire. There'll be noise here. If it's a bad wire or a bad connection, we'll have unwanted noise. This can occur during capture, storage, transmission, processing, or conversion. But noise can also mean that signals that are random, and they can actually be introduced intentionally, which is something that a lot of synthesis does. Signal processing noise can be classified with statistical properties. I'm not going to go into like mathematical details today because we've only got 2 more hours. So these are the examples I wanted to show you guys today because I wanted to implement them in C major. We've got a white noise, pink noise, and brown noise, and I'm sure a lot of people are sort of aware of how that sounds. And how do we trigger this? With MIDI. So we need that burst of white noise to emulate the guitar string being plucked. So the idea here is, I'll just grab this. What we want to happen is when a user presses a key, a little noise burst will occur. So we don't want someone to keep this held down and continue to have this noise burst. We want it to sort of blip on, blip off. And we're going to implement this with a noise gate. We will set the gate to be open for a length of time. So actually with the Karplus strung, we're going to use the frequency of the note to determine this. So if I check out branch 1 quickly, this is part 1 MIDI for everyone following along. And I will go back to duplicating my displays and keep changes. Okay, brilliant. So I'm going to rewrite this patch with you guys as well, don't worry. But let me just show you.
Sorry, what was
Yep.
the repo that you should get, or the directory that you should get from Git?
Yes, it's on GitHub. It's on our Dynamic Cast repo. ADC23 it's called. There should be some links online.
I'll post a link in the Discord channel.
Yeah, if you guys are on the Discord channel, or if people could go around. But while that's happening, I will just show you this quickly. Is everyone good? Everyone got that? Okay, cool. So this is what we're going to be writing in a minute. This is our part 1. And what you'll hear here is, you see we've got no knobs, we've got no annotations, so we can't sort of edit what's happening here. And you'll hear a blip of noise now when I press the key. Like that. Sounds great, right? That's pure white noise. And that is our source. As you can see here, I'm using a standard library tool for this. Okay. So if I just open this to the side and make a new folder called Karplus. And create a new patch. And what I'm doing here is creating an empty patch so I can code this along with you guys. Okay, so hopefully by now everyone's used to seeing this. This file was auto-generated, etc., etc. So what I want everyone to do is get rid of that. So we've got like a blank screen like that. What I'm going to do while you guys are doing that is I'm going to type in graph main. This is something I've been explaining ad hoc while I've been going around the room, but what we do is we add this main annotation to this first graph. So this is a special key annotation that the compiler is looking for, and this basically gives an entry point for the compiler so it knows to go, aha, this is where we're starting. I will execute, this will be our endpoint for internal input and output, this will be where we have our nodes, and this will be where we connect everything together. Fantastic. And then we'll write in, with the correct syntax, an input event. And instead of taking in a sort of a float value or anything, we're taking in this std MIDI message. So this is what's encapsulating the MIDI message. So we'll type in std MIDI message, and we're going to call it MIDI in. So that's our keyboard press, and then what we need to do after that is have an output. So we'll do an output stream. So as I explained earlier, I'll explain it again now. So the input event is basically we're listening for a keyboard being pressed, either on screen or off screen, and then output stream is the audio coming back out in a continuous frame-by-frame manner. And there's our first patch. We've got an input, we've got an output, and now we need to do something with that. So what I want to do is create our first processor. And this is where we're going to do some, again, processing some DSP of some form. And I'm going to make this thing called a MIDI gate. And what I want to pass into this MIDI gate is some events. I'm just going to make sure that I get the syntax correct here. The joy of a live demo. And as Alex explained earlier with the MIDI format, we have this section called note on and note off. So that's what I'm passing in to this processor. We want the note on and the note off value. Put event float. And then what I'm doing here is defining the gate length, as I explained earlier. What we're doing here is telling the gate how long we should be open before we stop emitting white noise. So we don't want it to go on forever, as I was saying. We want those blips that you all just audibly heard. And then obviously we want to output something from here. Like this. Should probably put this together like that. Okay. Brilliant. And as mentioned before, we've got these events. So I'm going to retype these and talk through them as we do them. Event in. Std notes, note on. And we're just calling that E just as an arbitrary thing. So what I've basically done here is I've taken in this note on event. I'm passing it through an event endpoint handler, and I've got to tell it to do something. So what we want with the note on is to trigger a gate to like a Boolean value to say, so we want 1 for it to be open and 0 for it to be closed. So what I've got here is I've defined a variable called active note, active notes. I'll do it down here to stay in line with what I've already got written, active notes. And we're going to set that to be closed for now, so it's a 0. And yeah, it's very simple from there. What we want to do with the note on is we want to make active notes be 1. So we do that with our nice simple syntax like that. So now, if you were to run this patch, nothing would happen because we've not actually connected the nodes up yet. But if you run anything for this processor, it would take the MIDI in, and you would just change this active notes value. You wouldn't hear anything, obviously. We've not connected anything up yet. And then what we want from there, now we've told it to be open, we need to tell it how long to be open for before we shut. And that's what we're going to do with gate length. And this is from the value that we pass in. So what we're doing here is we're setting up a variable called gate duration in samples. And let's do that quickly. And we're doing the exact same thing as we were doing up here. We're basically calling the gate duration examples to be the gate length. And that's all the events sort of handled. So we've pressed the MIDI note, we've told the gate to be open, and now we've also told it how long it should be open for based on some maths we're about to do that tells us the frequency of the note we've pressed from the MIDI message. Okay, and this is where our fun MIDI gate exists. So I'm just going to copy this in very quickly. So if you remember from the earlier patches, we've got this void main, and this happens in an infinite loop. So I've written this if statement here this is our noise gate in action. We've gone, if it's greater than 0, it's going to be 1, so we're going to be open. So what we want to do is output this and tell it that it's open. And then we're going to be open for the length of the gate duration in samples. And then once that's less than 0, we're going to bring active notes to be false again, so we're closing that noise gate. And that's what's happening here, basically. And that is the processor for the MIDI gate. So we've got everything we need to make this MIDI gate now. The only thing we're missing is the frequency from the MIDI message. We don't have too much time, so I'm also going to cheat and do a cheeky copy and paste here. But the idea being is I'll give you guys a couple minutes to catch up, and I can help people / take questions. So we've got this thing called a note selector. And we've done a very similar thing here of what we did with the original processor up here. We're taking in our notes on and pitch bend values this time from the MIDI. And then we're outputting a note frequency. So basically what's happening in this is we're taking in our note on, we're taking our pitch bend, we're using our standard library to convert this note into a frequency. And if you've got a MIDI instrument that can do a pitch bend or has like a slider on, you can see this in action. And it will change the length of the note. So one thing to mention here is the length of the... No, actually, I'll explain that later. Let's just do this for now. So if I run this... We've got the patch again. We've got a keyboard that pops up. And we don't have any sound. Exactly. So nothing happens here. Yeah, but we've got our nice keyboard on screen. So what we need to do is hook everything up. I'll keep that open for now. So we've made our 2 processors that we need. So we've got node gate. And we're going to make this equal the MIDI gate we just made. And then we do node. So this noise source is coming from our standard library, which basically just means we don't need to generate white noise ourselves. Like that. And now we're going to do our connections. I can't remember how I did this in here. Hang on. Yeah, okay. So this is the syntax I was talking about earlier. So with connections, you can either use the word connection and do things like this, and then you have to retype every time you want to do a connection, which isn't always the most useful. If you want to set all your connections at the bottom, maybe you do this. And now that means that you've encapsulated everything within this, these curly brackets to be a connection. So we can do our MIDI in here. We're not going to put a space there. And we're using this STUD MIDI MPE converter to make the message. MPE converter, like so. And then what we're doing is we're telling that to go into the gate. Cool. And then we need to connect our noise source. Connect that to the gate. And connect this up to the output of the output stream. See, I can't even get my camel casing right. There we go. There we go. Gate.out. The joys of a live demo. Okay. And then this final section is for the note selector. And this tells the gate how long it's got to be open for. So I'll just copy this in actually. And I'll move this off to the side. Okay, great. And that should mean that this works. And we've got that burst of white noise again. What you'll also notice is what I've added to this note selector is this console logging. And this is just a method of actually looking at the values that you've created here. So if I press an A note, you'll see that it's 440, which is what we want. So the gate length is going to be open for 440 samples, basically. Let me just leave this on screen for you guys to have a quick look at. And that's it. That's our MIDI gate. That's that all typed out. So let's move on to the delay. So let me just, actually I won't flip back to the code because it involves changing the screen size. But one thing that maybe you've noticed while playing with this thing is it doesn't matter which note you press on the keyboard, that blip is always the same like pitch, right? We don't have any pitch happening. That's because we're only outputting white noise. We've not actually done anything to it yet to actually synthesize anything. So this is part of what a delay line will do. So in the Karpus-Strong algorithm, the length of the delay will determine the pitch that's played. And this, the idea of this delay is it mimics the string vibration and the decay over time. So I just wanted to add in a little bit about a buffer because we're going to be adding in a circular buffer to do this. So a buffer is a region of memory used to store data temporarily while it's being moved from one place to another, like generally speaking. And we need methods to write and read to the buffer. And this is done with the read and write indexes, which I've put in these fun colors here. This is just a pointer to say, we're at index 0. We're reading from index 0, and maybe we're writing to index 0. So the only thing that's going to change from this slide and the next slide is I've made it a circle. And this is the circular buffer. This is a data structure that uses a fixed size buffer, as it were, and connects end to end in a circle. And as it's fixed sized, we're going to take out the oldest item of the buffer. We're going to push that out when more data is added. The queue is, so this is like a first in, first out buffer, FIFO buffer. We use the same method to read and write to the buffer using pointers of the data. There's this sort of technique of memory allocation. It does have benefits, especially when you're working with a lot of data in real time. As more data is added to the structure, the old data will be removed, so no data will ever be needed to shift. Okay, so that's enough talking. Let's go back to typing. Will I change the display type? If anything, this is a good advert for the settings panel on Windows 11. So what I need to do now is get rid of my changes. Just got 2 such changes, yeah. And I'm going to flip to part 2 delay. And I'm going to open the correct VS Code panel. I'm just going to zoom this in a bit so I can read it on my screen. Okay, brilliant. So this is what we're going to be typing out now. As you can see, the delay, it's sort of changed a little bit. Instead of going straight to the output, we're going into a delay, and we're going to multiply it by feedback, put 1 frame of delay in, and put that to the output. So this sounds like this. We're also going to add some annotations as well. As you can see, we've got a feedback annotation, and now that sounds like a string, right? Like a little bit. You can hear it. You can hear that sort of decay as the string stops vibrating. And we've got pitch. A bit tinny, but we'll get to that. Okay, cool. Actually, what I'm going to do is just switch back to the original branch. Copy what we've already done. And go to this new branch. Put that to the side. And create another new patch. I'm sure there's a simpler way of doing this. Create patch, brilliant. So now we've picked up where we left off. I'm going to make a simple edit to this before we get going. I'm going to remove the console logging, but you can keep this in if you want to look at the pitch changing and stuff. I'm just doing this to make some space on my screen. So I think I'm going to start by writing this delay processor. So we'll do the same thing again. We're doing processor delay. We've got our curly braces. Let me just show you the finished code quickly. Yeah, nice and simple. So we're just working with floats now, basically. Input stream float in, and then we're going to output some values as well. But obviously this is going to go through our circular buffer and come back with a delay. Oh yeah, I should also mention that the delay length here. Oh, I didn't define it as a float. Perfect. So there's our inputs and outputs for our delay processor. We're going to take an input stream of data, output a stream of data, and then we're going to take an event that tells us the delay length. And as I said earlier, this is based on the note to frequency that you get from the MIDI note that you're playing. I'm actually just going to copy this in line by line. Let's look at these 4 lines first. By the way, the reason I'm doing this is, one, because I can't remember the whole patch off by heart, and second, so I can just talk through each line as we're going. So as I mentioned earlier, we're handling our input event. We've got this event handler. We've called it delay length, and we're taking in the delay samples. What I've done down here is mention this wrap type. So this wrap type is an integer of a set length, basically. So I've set a max delay length to be 1,000. And if anyone's sort of used to JavaScript land, you'll know the let keyword is a constant. We could change this if you needed it to change. It could be var as well, and that means that it's changeable. But in this context, we want it to be let because we want this to stay. I set this to an arbitrary length, which means that we'll never, as I mentioned earlier, we need the circular buffer to be a specific size so we can loop back around and start rewriting. And this is what's happening here. So we've made a float, we've got this max delay length, and we've set the float to be that size. And we've got these wrap types, which is our pointers to the read and write positions that's happening here. And what's happening with this event, I'm actually going to bring it down so it's easier to show you guys. This is just my syntax OCD now. What we're basically doing is we're telling the read position to be a set length based on the delay samples. So this line is basically taking the frequency of the processor, dividing it by the amount of samples, and that's where we're going to read from. And now we write our main loop as previous. We're not passing any values in, so we've got closed brackets, and then we're going to go into our infinite loop here. Yep.
Where these processor frequency comes from?
This is a fun thing about C major is when you instantiate process. Let me just run this quickly. Play some hold music while it loads. So anyway, as it's loading, the processor.frequency is a keyword, so it's looking for what frequency is set to this processor. So if you come down to your audio device settings in the panel, you'll see that my sample rate is set at 48,000 hertz. So this is just a way of getting to this value. Yeah, apologies for the very minor sort of explanations here. It's just because of time. I don't have time to go through everything, but please keep asking me these questions as we go. So we've written our infinite loop, and now we need to do our. It's the same. I mean, if you guys have ever written a circular buffer, you'll notice that this syntax is very similar to what you've done previously. Hopefully, I'm just going to paste it in here. Get rid of this. And what we're doing is we're telling our output to the world. As I said earlier, processors can go through and out. We're telling the output to be where our read position is. So we're reading from the buffer and taking it to the output. And then based on where we've set our write position, we're going to set that to be our input. And then we just advance. We advance the read, we advance the write position, and then we keep going. And this happens in an infinite loop. So now we've got that processor written out, we can make some connections. So you'll see, if you look at side-by-side comparison, you see that there's not too much that's changed here. I've added some extra connections, and I've also added this feedback annotation as well, which means that we can choose how much feedback there is. That basically changes the length of the delay, as it were. So I'm going to add this in first. So this is an input value. And we're going to use this special, if I can spell the word feedback, we're going to use this special annotation. And this tells C major that we need a knob on screen of some form. I'm just going to copy this straight in, again, for time. But please type this out as it comes. There we go. And that will now show on screen. I'm actually not sure if it will. I don't know why it's taking so long to load today. And there we go. We've got a knob on screen. It's not attached to anything right now, so it won't do anything. But you see I've just set an arbitrary value here. You can change them in a max, and you can initialize to be from wherever you want. So that's now that knob on screen. Okay, so what we did earlier, we've been defining all these nodes, so now we want the delay node. So we do node, not noed, node, delay. And it's called delay, because our process is called delay. Brilliant, and now we need to do some more connections fun. So I'm actually just gonna get rid of these and copy this in, and I will talk you through what's happening here now. Brilliant. So as well as the gate needing the length set by this note selector, we're doing the same thing with the delay length. You'll see it's like an arbitrary value, and what I've done to save space is use this comma annotation here. So this is MIDI in, we're going through our MPE converter to make the values that we need for the note selector, and then we're going straight into our delay length and gate length. And then after that, we need to go into the gate event in, as earlier, to say, hey, we've got a note on, we want you to open the gate. We're doing the same thing as we were doing here earlier. We've got our white noise, we're going to the gate.out, output, and we're multiplying by the gate.out, sorry, that confused me for a second there. So that's our 1 or 0 value. If it's 0, obviously we're just multiplying the noise source by 0, so it's just going to output nothing. And when it's 1, it'll just be the noise source. And that's going to our delay.in here, as you can see, is an input stream. And then what we're doing from there is we're multiplying this feedback. This is why I've set it to be 0.99 max, by the way, because otherwise we'll have an infinite feedback loop. Now this annotation here is to tell C major that, okay, we just want to wait for 1 frame, and then we want to put this into the delay in, and that again stops the feedback loop. And then we're going to go from the output of delay straight to the output. And if that all works, and we wait for it to load, you'll see we've got this GUI with the feedback, and we can make a noise. And now we've got not an annoying blip, but instead we've got a short blip with the low feedback, or a longer blip with, that sounds more like a, I don't know, like a short resonated body sort of string instrument, right? And that's part 2, that's the delay line. Okay, again, I'm going to leave this on screen, give everyone 5 minutes to sort of catch up. Please refer to the branch code as well, and again, I'll come around and answer questions, okay? Okay, so this is the patch we've just created again. hope that woke you up. I'm sorry. That was loud. So we've got our delay, we've got our noise source, we've got our string excitation. And this is what we were talking about with the guitar. We're sort of seeing the string rivation, we're seeing this decay. But unfortunately, I mean, listen to the note. Like, it's really like quite tinny, you know, you don't really want all those higher frequencies. So this is where part 3 comes in. This is where we talk about filters. And I'm just going to go back to my slides. Can you guys see the filters? Yeah, brilliant. Okay, filters. So as we've just established, I mean, I think it sounds great, our instrument, but I think maybe a million producers would probably tell you that that's not okay and the mix sounds awful, so please add some filters in. This is going to be a very high-level overview of filters, by the way, simply because I've sort of only got 15 minutes per section. So a digital filter is like a mathematical algorithm that operates on a digital data set, e.g. audio data, in order to extract information of interest and remove any unwanted information. So in this case, it would be all those high frequencies that we're hearing at the moment. So the 4 common types, I'm sure everyone's aware here, but we've got high pass, low pass, band pass, and all pass. And we can sort of divide digital filters into 2 categories. So we've got infinite impulse response filters and finite impulse response filters. And as the name suggests, each type of filter is categorized by the length of its impulse response. I'm actually not going to show any mathematical equations today, which maybe everyone's whooping a cheer of joy at that. I just don't have time, I'm afraid. So I just want to give a quick high-level overview of IIR and FIR filters for everyone. So when you see this hopefully in the talks in the next few days, you can sort of understand what people mean by this. So infinite impulse response filters, generally chosen for applications where linear phase is not too important and memory is limited. So they're easy to design, easy to implement, and they involve fewer parameters. So it's less memory and therefore less computational complexity. The disadvantages here is for mathematical reasons. They can become unstable and they will accumulate rounding and noise error over time, basically. And an IIR filter example is like a Butterworth, Chebyshev, all of these nice examples, Bessels, elliptics, etc., etc. FIR filters, finite impulse response filters. These are generally chosen for applications where linear phase is important and a decent amount of memory and computational performance are available. So they're stable by design, again, maths. There's no distortion because it's a linear phase, and they are easily customizable. But obviously disadvantages there, you know, depending on what you're running on, they do take a larger storage requirement and they're computationally quite expensive. I apologise for that whistle-stop tour of filters. So we're going to go back to programming now. So this is part 3. Hang on a minute. I forgot that I need to change my display. And we're back to duplicating, so I can see what I'm typing. So what I want everyone to do here is, well, you guys can keep on your patch because we're just going to add to it, and I'm just going to discard these. We're going to go into part 3, filters. And what we're not going to do is look at the wrong patch. Okay, so this is what you'll see if you've checked out this branch, or if you've got it open anywhere else, you'll see that we've added a load of filters, basically, and this is what we're going to do with this example. So I'm just going to run it so you guys can hear what it sounds like. It's very similar to what we've just heard, unsurprisingly. Okay. It's not going to work. What's happening here? Hang on. Part 3 filters. There we go. Someone set the gain to be 0.1. It was me. I did that. Apologies, guys. If you've checked out the repo that's there, please change that. So I don't know if you guys can hear the difference from the one we played about 10 minutes earlier. We've got more of a sort of refined sound, as it were. We sort of low-pass filtered all those high-end frequencies. And we're starting to sound a bit like a guitar now. Cool. Let me make my patch again. Please, without the demo. Okay, fantastic. So this is the code that we were just looking at. This is just for my own use here. So let me just close that patch. Okay, so this is what we had previously, and I need to put this to the side. You can see that I've got rid of this feedback knob as well. So what we're doing here is we're not actually going to implement any filters today. I just want to add some filters into the sound so you can then either change them, modify them, or add in different filters. So part of the C major standard library is one pole and Butterworth filters. So that's what we're going to use today. I'm not going to go into too much detail here, but I will answer questions as they come. So as you can see at the bottom of the delay, I've added these two nodes. And we've got a filter, I've just called it filter, this could actually probably have a better name, and node low pass as well. And we've also added a gain, and that's what tripped me up about a minute ago. So this is all we're adding in this section now. So we've added the two filters and the constant gain. And yeah, it's at 0.9F, not 0.1F. So we need to connect these up, basically. What I did in the previous example was set this feedback annotation just to show you how to start with annotation, but I'm actually just going to set this to be a set length. There's no real reason for this. I'm just doing this to save a bit of screen space and everything. You can keep this as a feedback event if you want, a value if you want. No problem there. Oh. I'm just going to copy and paste this all in. And I'll put this in here and just comment this out quickly. And the only reason I'm doing this is so I can immediately show you guys some comparisons. So as you can see, the top line stays the same. Noise source, dot out, gate out, it's still going to the delay in. That's because we're not filtering, obviously, our events happening there. From the output of delay, we're going into filter.in. And this is this is a closed thing. We're not actually going to see this because it's happening in a standard library processor. We're going out to a gain, which is this one here. And then we're outputting. Oh, sorry, my throat's killing me. And then from the noise source, so what's happening here is we've actually added in the noise source into our final value as well. And this is because we want a bit more of an excitation of that blip. So we actually want that initial blip that we made in part one, but we want to get rid of some of those higher frequencies. So we've got noise source going into the gate, going into the low pass, taking the output. So this is just telling it, again, that's the 1 or 0. That's telling it if it's off or on. It's going into our low pass to get rid of some of those high frequencies. We're going in from the output of that, multiplying it by that same gain, which is, again, 0.9 in this case. Was it 0.9F, and going into our output. And if I run this. Wherever it wants to run. There we go. I've left the feedback annotation on here, but it's not actually connected to anything, so we can go ahead and comment that out, and we'll see that it'll hot reload and disappear from our screen here. Just for ease, I'm also going to get rid of this. And hopefully this time we'll hear something. There we go. Okay, great. So if you guys want to go ahead and add these filters in, it's these two here. It might be worth actually linking to our standard library so I can show you guys what these all mean actually. So again, I'll give you guys another 5 minutes. So we'll come back at about 2:45/10 and we'll continue on to the next part, which is going to be polyphony and the final patch. Okay? Cool. Okay, great. Let's keep going.
Sure.
Just get this ready. Actually, I'm not even going to clone it this time. Watching me live push to the repo. And that's me fixing my error from earlier. I don't even know when I would have set it to 0.1. Like, that makes no sense to me. I don't know where that 0.1 value came from in the constant game, but that would be me last night, like panic typing these branches out and then not. We didn't change. We didn't have time. I guess we could rebase it later. Yeah, well, timing wise. All right, guys, thanks for bearing with me while I went through some questions. That was filters. Hopefully that'll give you some groundwork for later talks later in the conference and stuff. So this is the final part of this now. We're doing well on time. We've got 40 minutes, which means that we get to talk about testing, which I hope is everyone's favourite part of any workshop, is writing a unit test. Woohoo! We've got a lovely QA engineer, Emma, here to tell us why testing is important, which, by the way, she's doing a talk about tomorrow, and I would highly recommend going because it's very funny and makes me want to write a test. Okay, so one thing you may have noticed while you're playing with the patch, maybe not, obviously, with the if you're using the VS Code panel, you won't be able to press on keys like I can, but if you try pressing on 2 keys, you may have noticed that it's not working. Like we're monophonic right now. So monophonic basically means that it's one note happening at one time. So we press a note, wait for that to happen, we can then trigger the next section. So polyphony is multiple notes. Makes sense, right? So it's the combination of 2 or more tones or melodic lines, and that's how we define it in music. So our synth needs to handle that, really. I mean, we could just leave the instrument there and we could just have a guitar synth that only plays like a solo or something to some sick Led Zeppelin, and that's great. But I know a lot of guitarists like myself actually need to play chords. So for this, we use a thing called a voice allocator. So this sort of graph here, this sort of shows a simple voice allocation algorithm. So voice allocation is like a voice circuit, and this is the number of notes able to be played at any one time in a polyphonic synth. This comes from hardware land. Say, for example, so the number of voices they had is the number of notes you could play all at once, and this has sort of come over into software, and we still call it voices. So say a 3-note chord is played. If you play C, E, G or something on your keyboard, these notes are assigned to voices 1, 2, and 3, respectively. And then in the digital world, we've recreated this basically with the same voices, and they dynamically assign to voices to played notes. There are some algorithms that do this, that make this quite effective. I'm going to use the standard library to do this, and we're going to use 8 channels that are dynamically allocated. So what I'm going to do is flip back. So this is... If I go skip, this is branch 4, and this is part 4 polyphony. So everyone, I'm not going to go through copy and pasting code, because the only thing I do here is add a voice allocator algorithm. So this code is going to look a little bit different for what we've just made. As you can see, all our nodes have gone. What's happened here? We switched screens. Thank you. I like how you all just played along with that as well. Thank you. My ride or die is saying, yeah, that looks different. Yeah. Yeah. Does it look different now? Can you guys read that? Shall I bring it up one? So now all of our nodes have gone, and what we've done is we've created another graph. And what you'll notice in this graph is that all of the nodes that we've originally defined and written and gone to different processes are now here. And that's not changed. And what you'll notice here is the connections are all the same as well. So this graph is handling our polyphony. So let's go through this. So what I'm doing here with this node is I'm instantiating 8 arrays of this graph. So there's like 8 voices happening all at once. So the same thing, you play 8 notes, it'll allocate from 1 to 8. And then we're using our voice allocator to do that. So we've got this thing called voices and voice allocator. And what you'll see, what I've done here is I'm taking the MIDI in, I'm putting it through our MP converter again, and we're going straight into our voice allocator. And once that takes the event out and goes into our voice here, notes in. So the topology of this graph looks exactly the same. Again, I'm skipping over this because we don't have too much time to actually implement a voice allocation algorithm in the time given. And then what we've done here as well is add these annotations. So I've brought back that feedback annotation we had earlier. You guys remember, you probably already kept it in. And what I've done here is add 2 more annotations. So it's impulse length and filter. And that basically means that we've just got a little bit more control on the default GUI, which means that this thing's a little bit more interactive, because when I wrote this, I realized I had nothing on the screen and you could only make one type of noise. So if I run this, what I'm going to do now as well, so this is our final patch. This is where we leave our C major. What I'm going to do is show you it, and then maybe show you some edits you could maybe make, and maybe just to get you guys inspired, because I want you guys to have a little bit of a play in this, make this instrument your own. And that might mean like changing the filters and things like that. So if we have a look at our VS Code panel, we now got 3 knobs on screen, which is our delay length, our filter frequency, and our feedback. I'll just keep it here as well. And once again, is it also still 0.1 in here as well? It is, look at that. Well done, me. Now it will make a noise. What's going on? Okay, just for ease, I'm going to switch back to main because this is what's also on main as well. And we'll run this again. It'll be a proper laugh if this doesn't work. Maybe it's the keyboard. Yeah, I do. I just want to... Yeah, now we're getting a noise. Yeah, it is. I'm just editing some of the settings as well. There we go. Yeah, sorry, my volume settings also changed as well in between, which means that the other branch is probably also working. So it sounds like earlier we've not changed the filter or anything. We've still got the same initial values, but now I can play a C major chord. Brilliant. Do you get the pun? Do you get it, guys? Come on, work with me. So give that a go. Check out that branch, or if you want to copy the code exactly, I can either put on the connection here, or I can put it back onto the voice, wherever that's gone. Oh, that is the voice. I can put this connection on here, or I can put on the voice graph, whichever one's easier. One final thing I want to show you, because I've had a few questions about this today, is this graph topology. So I explained this obviously earlier with a very simple example. I did that in, we took a value in for the gain, the stream in for the gain, had a gain processor, and had the out. Obviously, this is way bigger now. And you can actually follow through, just like in Max, you can follow through everything that you're doing, and you've got the following the gate in, following the gate out, and you can see this is where we sort of have our noise source. So this is where the white noise is. You can follow this all the way through. So if you're more of a visual learner, I am myself, I actually really enjoy looking at these graphs. Or if you want to change a connection, this will hot reload and you can see the new connection. And the nice thing about this is if you want to change a specific thing, like this noise source, I go, oh, I want to go to this line. You can click on it and it will take you there. So if you were listening earlier, you'll know that we have different types of noise source. We can change this to be a brown noise. This will sound like this. You see it's got a different timbre, a different style. This is because the noise source has changed. And we've also got pink. So if you want that lo-fi pad vibe, give that a go. And this is the pink, and it's got a bit more like high-end excitation. So you might need either a higher order low-pass filter or something like that. So give that a go. Again, I'm going to give 5 to 10 minutes for this because we've got about half an hour left of this workshop, which means that we've got time to talk about testing again. Okay? Brilliant. Let me put that on there.
Right. Everyone's ready? Talk.
Yeah.
Once you've got past the intro, it's gone to the good bit, tests.
Tests.
Tests, very important. If we're going to send you out recklessly developing things, you should at least have some idea how to test them as well. But yeah, I'm not going to go too much into the C major syntax of it, but just a couple of kind of core concepts of testing. This is on the main branch. You'll be able to find all this. Have 2 tests. So here we've got something called test function, and we've got a function that returns a bool, and this is just all internal to itself. So it's adding a vector to itself and checking that it's got the same thing. So by itself, this isn't particularly useful. But if you had some kind of logical processor, and you could say, right, if I do this, I expect to see these results. And if that returns true, so that's sort of the all true here is saying that all of these values are right, then that will return true and say this is passed. True becomes pass, false becomes fail, and if you run patch on one of these CMAG test files, it'll open up. No, I don't. What are you doing? Then it'll do a Windows thing and not work like it did for Mac.
Echo.
There we go.
Haha. Comparison failed. Yeah.
Yeah, okay, so get to that in a minute. So I'll run test and I'll show you that one of them has passed, which will be this test vector add one. Because we can follow that through logically, see it works. So test function, good for logical processing. The other is this run script, funky one. So we've all been using CMajor from the VS Code extension. There's also terminal ways to run it. And this is one such way, which is essentially giving it some parameters, so sample rate, block size, length things, and it's talking about this test1 folder. So this test1 folder, we've got a couple of bits of JSON. So here's some kind of, there's a MIDI note, there's where it's occurring, there's parameter filter, parameter feedback, and then a WAV file that is what we expect to get out. So this is essentially doing a sample by sample comparison. That only works because this is fully deterministic. So if it could not be, depending on the noise generator we use, the CMajor standard library noise generator is deterministic, so it'll produce the same thing every time. Some other ones aren't. They produce better randomness, but they don't have this useful feature for testing. So this is going to essentially trigger it as defined in those JSONs, compare it to this, and say that it's not working. So yeah, max dB diff exceeded, blah, 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 blah. All these thresholds, probably to do with that 0.1 gain that was flowing around. Let's see, what was that? 9.9 maybe? Oh. What? No, can't remember what the settings were when this test was defined, which is, no, I definitely don't. Yeah, so essentially that's kind of the other way of testing audio. If you've got it fully software, fully deterministic, you can do a sample by sample comparison. It's kind of the most stringent test. So if you wanted, you could kind of break it down a bit more, maybe do a third octave band comparison with some threshold, and it's kind of, it will be-ish the right thing, which is kind of a bit more lenient. But yeah, and that would probably help us avoid this error where I can't remember the settings that we define the thing at. And yeah, I'm not going to go further because I'll be here for 50 minutes tomorrow, going way too far. So yeah, that's said here. What I wanted to say here.
Thanks, Emma. Thank you. Okay, so that is the end of the content that we have prepared for you guys. I'm just going to go back to the slides. We spent time on the slides, so I will show them. That's been my... yeah, these are the unit test ones. We'll just go through this. So thank you guys all for coming. We've got about 15 minutes left of this workshop before we go to lunch, I assume is the next part of the day. I'm around for any questions. You can ask anyone here, but just play with the patch, have some fun with it. And yeah, if there's any more questions online, please feel free to ask them because I will be monitoring the laptops as well. So yeah, thank you very much, guys. Thanks for listening.